name is Jacob Hurst, and I'm just going to be presenting on Storm Peak Labs and the data analysis I've done so far, including methodology, instrumentation, pretty much everything I do it for my research position. So, my supervisor is Naruki Hiranuma, um, and he works in the Environmental Sciences Department at West Texas A&M. And yes, let's go to the next slide. All right, so basically the location that I was at whenever I started doing my research position was 1 month basically into me getting the position. We took a trip up to Storm Peak Labs, which is 10,000, 10,500 feet, or 10.5 thousand feet, you know, um, above sea level, and it's basically a laboratory settled up on top of a mountain in Steamboat Springs, Colorado. Little background, I was able to attend the setup, and I actually helped in the gathering of our summer samples for the SPL um, basically project. Um, and in this trip, I was able to gather SPL Experiment A and SPL Experiment B. After that, they sent a secondary group member up to the lab during winter. Should have been, I think, in January. They sent my coworkers up there, and they gathered the data for SPL experiments 1 through 59. Okay, well, a little more background is for our sample backgrounds, basically, samples were taken so each experiment ran for about 10 minutes um, at the through the PCVI impactor. All the samples were taken using a two-stage mini impactor on aluminum substrates with a 50% cut size of greater than 0.1 micrometer and greater than or equal to 0.5 micrometers. Um, Note that our mini impactor does produce two samples at one time. One is taken on a 0.2 millimeter nozzle and the other is on a 0.6 millimeter nozzle. Um, in these samples, we also took cloud residual samples, which were pumped or put through a pumped counterflow virtual impactor, which is the PCVI, was utilized, and it had a 50% cut rate at greater than or equal to 25 micrometers. Um, Air masses were also taken into account, which basically just does the back trajectory analysis of where basically the wind and airflow is coming from. So basically on the right there, uh, that line just shows that our samples came from the west primarily, and we were able to conclude that they probably went over smelting factories, which contributes a lot to our chemical composition later on. I did forget to mention on the sample types, we do have a zero point 0.2 millimeter and a zero point 0.6 millimeter nozzle. And then we are also taking cloud residual samples and aerosol samples. So our primary conditions we're looking at right now is our residual samples, and then we're looking for cloud conditions, so in cloud or out of cloud for the aerosol samples. All right, a little bit more background. So I use an SEMEDX scanning electron microscope with energy dispersive X-rays, primarily for my work. Little background on those. On all of our samples, we have taken 1 to 200 particles imaged and analyzed. A little bit of background how the SEMEDX works. The electron beam knocks the K shell electrons out of orbit, causing them to emit an X-ray, while the external shell electrons fill the space. Just because I kind of like the math a little bit behind it, we can find the X-rays are identified using their energy. So I just threw the energy equation in there. Sorry, I had something else. I was going to talk about the scanning electron part. So basically, to get the imaging, we just use a scanning electron beam. So it just basically in like a line pattern shoots an electron beam across, and then reflections off of that are how we get our images. Okay, another machine that I use is the cloud imaging probe. Um, that's just a little diagram of how the cloud imaging probe works on the right. This works by the shadow images of particles are collected after passing through a collimated laser beam. They are then projected onto a linear array of 64 photodetectors. The particle images are then reconstructed from the slices of data taken by the photodetectors. Our particle sizes are then also taken and distributed into size bins, which increase by 15 microns per bin. The laser specifications are 658 nanometers and 30 milliwatts, which is in our red color range, which is actually that is the ideal color range for this kind of scanning or this kind of analysis. So our particle counts are then distributed into those bins, and they're just based off of the sizes that are observed, which I actually just said a minute ago. I don't know why I have that there twice, but we'll head on to the next slide. We've got the Raman spectroscopy. Raman utilizes the inelastic scattering of photons emitted from a laser. The photons that are emitted excite the bonds between the different chemical compounds, and rho vibrational angles are measured and then used to identify the different types of bonding. This is typically done to analyze what types of organic bonds are present inside of our particles. You can also see other types of bonds, like metallic bonds, just basically like any type of bond between um, elements. So, all right, this is just to be my size analysis methodology. To the right, I have an image that I've taken on our SEM-EDX. I know it's not the best quality. I wish it was better, but our SEM-EDX is not very new. It's like over 20 years old, so it's not very good, in my opinion. All of our images were taken for size analysis were taken on our SEM-EDX. I then import those images to ImageJ, and then I measure the cross sizes, or the cross section averages, and then those are graphed. Note most of the particles are only a few microns in size on average. And to the left, yeah, I just said we just have an image of particle 45 from my SPL 49 0.2 millimeter sample. Little other note, yeah, rough estimation of the size on that is about 2.75 like microns squared. So yeah. So our chemical composition methodology, on the right there you see that's just the equations we use for how we determine what category to put the particle into. Atomic percentages are calculated using the like electron dispersive X-ray function of our SEM-EDX. We then record the atomic percentages found that are manually selected our 15 elements that we are primarily interested in, which are also listed there on the right. The atomic percentages are then used in the equations in the image. These calculations have also we have also been taking background readings of our aluminum substrates, and I'm subtracting those from our actual particle like EDX output, like our atomic percentage output. And the reason I'm doing that is to hopefully counter any leakage coming from like the aluminum into our readings. So, let's see. So now we'll go on to the Raman spectroscopy methodology. Our Raman data was obtained at Texas A&M by one of my previous associates. I conducted the data analysis um, of this with the help of this associate too. I don't know why there's an A there. Sorry about that. To identify the different bonds present, we initially had to look at the individual particles and the peaks that they produced. We then identified those peaks using a book of known peaks and peak locations. From this, we were able to roughly get what organics are present and what types of bonds are present inside of the particles. So here's going to be my cloud imaging probe methodology. Our CIP was used in order to capture the size of our incoming particles. Note that this is also just from the ambient weather outside, so it does just account for everything. It'll also intake the snow particles and like snowflakes and stuff. For the CIP data, I need to utilize a sample list of time intervals, and then I just match them to basically the time periods we. Technical difficulty. My headset shut off. Um, yeah, I then would add those and get the total amount of particles present, and then so basically to make the graph on the right, I took the logarithmic value of the totals, and as we can see there on the x-axis, um, those are the particle bin sizes. So like that's why there's the less than size, but we can see that the most particles are found at like less than 15 micrometers, or yeah, microns. My bad. Let's see. We can also determine basically based off of the far right here, whether it is inside or outside of a cloud. Um, and we're going to do that to confirm our observed conditions that we have written down. So let's see, head on to observed results. All right, so far, I've been able to do SEM EDX analysis of 38 different experiments, and that's 100 particles on each experiment, and then that also includes the different nozzle sizes for the same experiment. So we could have like SPL 49, and then there's the 0.6 millimeter nozzle output experiment, and then there's the 0.2 millimeter nozzle output. Um, I can go into the PCVI in depth more if you want later, if you want to know more about it, because I realize I did not put much information about that. But I have also been able to complete the size analysis and chemical composition of all 38 of those experiments. I did the CIP analysis of them, the Raman analysis of them. Um, so basically, in general, in terms of results, I found that most of the chemical composition of SPL samples comes back as dust, which is going to be like silicon and calcium, and then yeah, those basically are going to be the primary atomic percentages present. We found that the sizes, as we confirmed with our CIP data, is obviously less than 15 microns. Um, I don't have the overall average of everything together, but that's what I found so far, or I've observed. And then, let's see, finally, we were able to observe quite a variety of organics present inside the samples using our Raman analysis. Um, I haven't actually drawn anything between the Raman and other areas yet of data. We're actually working on wrapping up the project a little bit. I have a few more samples to look through before we start trying to compile everything together and looking for similarities between samples and different machines and trying to figure out basically just draw conclusions of stuff. So I'm looking forward to doing that in the future, but so far that's all we have done. And that's the end of my slideshow. Hope you enjoyed it. I know I rambled a lot and I'm probably speaking too fast, but yeah.